So we are going to talk about the basis for tensor products of vector spaces using the universal property. If you aren't familiar with the universal property of tensor products, I've left a link in the description to a video I made explaining that, so you can check it out and then come back here. So let's suppose we have two vector spaces V and W, and they have basis EI and FJ. Now I've written this basis as EI for all I in some indexing set capital I. So this could be a finite basis, E1, E2, E3 up to En, but if V is an infinite dimensional vector space, it could also be an infinite basis, so there are infinitely many of these little i's in the set. Same thing with W. Now if we have these two bases for V and W, it's pretty straightforward to show using properties of the tensor product that EI tensor Fj for the pairs ij in this Cartesian product I cross j, this generates V tensor W. So this is basically saying that if we take all possible pairs, EI and Fj, those tensors together generate the whole tensor product. You can try to prove this for yourself, or I've also done it in a video in the description you can check with the timestamp for when I prove this particular result. So we know that these tensors, EI tensor Fj, we know that they generate the tensor product. But the question now is, are these a basis for the tensor product? Remember, the basis for a vector space is a generating set that's linearly independent. We already know that this is a generating set, so what remains is to prove that it's linearly independent. So let's recall what it means for a set to be linearly independent. A set is linearly independent if anytime we have a finite linear combination of some scalars times elements of the set, if this finite linear combination equals 0, then that implies that all of the coefficients, lambda ij, have to also equal 0. So I'm not writing the specific indices under the sum here, but the point is that we're summing over some sequence of pairs I, j, and the number of terms in this sum is finite. So this is a finite linear combination, and if this equals 0, then all the coefficients have to equal 0. That's what it means for the set to be linearly independent. Now before we get into proving that this set is linearly independent, I'm going to define another vector space. I'll denote it by F superscript I cross j, and this is going to be a vector space with basis vectors for each pair I, j in this Cartesian product I cross j. So this is a vector space with a new basis, and I'm going to call the basis vectors b sub I, j. So in this vector space, for each pair I, j, we have a basis vector. So the number of basis vectors in the vector space is equal to the number of elements in this Cartesian product I cross j. And each basis vector just corresponds to one of these pairs I, j. So with this vector space f to the I cross j, what I want to do is define a function f hat that goes from the tensor product, v tensor w, into f to the I cross j. And we'll define it like this. So we want to take f hat of some element of the tensor product. But we know that these pure tensors, EI tensor Fj, they generate the tensor product, v tensor w. So we can write any element of the tensor product as a finite linear combination of some lambda I, j, EI tensor Fj. So this is our element of the tensor product, and I want to send it to this vector space by moving this element of the tensor product to the sum of lambda I, j times b I, j. So what we're essentially doing is sending each pure tensor, EI tensor Fj, to the basis vector b sub I, j in this new vector space. Now let's suppose that this function f hat is well defined. And let's also suppose that it's a linear map. And we'll ask if this f hat is a well-defined linear map on the tensor product, can we use that to prove that these pure tensors are linearly independent? Well, let's say we have some finite linear combination of these pure tensors that's equal to 0. If this is equal to 0, then f hat of the sum of lambda ij, EI tensor Fj, well, this input here is just 0. So f hat of this whole input is equal to f hat of 0. And if f hat is a linear map, then f hat of 0 is always going to equal 0. But on the other hand, we know that f hat of this sum, by the definition down here, is the sum of lambda I sub j times b I sub j. So we just showed with this argument that this sum is equal to 0. Now here's the thing. In our definition of this new vector space, these vectors here are basis vectors, which means that they are linearly independent. And we just found a finite linear combination of these basis vectors that equals 0. If that's true, and if these are linearly independent, then each of the coefficients has to equal 0 as well. So we started out with this linear combination of the pure tensors equaling 0. And what we found is that lambda sub ij has to equal 0 as well. And that's exactly the condition for these pure tensors to be linearly independent. So what we just found is that if f hat is a well-defined linear map, we automatically get that these pure tensors are linearly independent. Our new objective is to show that f hat is well-defined and linear. So we ultimately want to define this function on the tensor product. But in general, it can be difficult to check whether a function on the tensor product is well-defined. So the way that we do that is using the universal property of the tensor product, which I've written right here. For every bilinear map from V cross W to some vector space, in this case we're interested in the new one we defined earlier, there exists a unique linear map f hat from the tensor product into that vector space such that f hat of V tensor W equals f of V comma W. Now, at the end of the day, we want f hat to be this function over here. So let's think about what do we want for f hat of EI tensor fj. Well, that's the same as this sum right here, except that we're just looking at a single term and the coefficient is 1. So what we want f hat to equal in that case is just b sub I comma j. And if we look at the equation over here in the universal property, what this tells us is that we want f of EI comma fj to equal b sub I comma j. So if this equation is true for our original bilinear map f, then the universal property tells us that this equation in f hat will also be true. So we have this first relation for f. Let's think about how we can extend this to a bilinear map on the Cartesian product V cross W. Remember that in general, we're going to look at an arbitrary element of V here and an arbitrary element of W here. But we know that EI is a basis for V and Fj is a basis for W. So we can write any element of V as some sum over some indexing I of lambda I times EI. And we can write any element of W as sum over J of, let's say, mu J times Fj. So this is an arbitrary element of V. This is an arbitrary element of W. Our goal is to have f be a bilinear map. So let's assume that f is bilinear and see if we can use this equation here to figure out what f equals on this arbitrary pair in V comma W. Now because f is bilinear, in particular it's linear in the first input. So we can write f of this sum lambda I times EI as the sum over all I of lambda I times f of EI comma sum over j of mu j times fj. That's our first simplification. Next, we know that because f is bilinear, it's also linear in the second input. So we can do the exact same thing again, which means we can write this as the sum over I and then also the sum over j of lambda I times mu j times f of EI comma fj. But we know what EI comma fj is when we plug it into our function. This is just equal to b sub I comma j. So this gives us the definition of f on an arbitrary element of V cross W. It's the sum over I of the sum over j of lambda I times mu j times b sub I j. Now we need to know that f is well defined, but here's the thing. We're defining the value of f in terms of the coefficients lambda I and mu j. But these vectors here, ei and fj, these are basis vectors for v and for w. And what that means is that every element of v can be written uniquely in exactly one way as a finite linear combination of the basis vectors like this. And similarly, every element of w can be written in exactly one way as this finite linear combination. So because these expressions in terms of lambda I and mu j are unique, we don't have to worry about whether the function is well defined, because these coefficients themselves are also well defined thanks to the fact that ei and fj are basis for their respective vector spaces. So we know that f is a well-defined map from v cross w to our new vector space. And because we constructed f by assuming that it was bilinear and using that to make the definition, it's pretty straightforward to check that this definition of f does in fact give a bilinear map on v cross w. You can go ahead and check each of the conditions directly using this definition. So we have a bilinear map f from v cross w to our new vector space. And now we can apply the universal property of the tensor product, which says there exists a unique linear map f hat on the tensor product such that f hat of v tensor w equals f of v comma w. So in particular, f hat of ei tensor fj equals f of ei comma fj, which we can check by this definition is b sub I comma j, just like we want. So using the universal property of the tensor product, we've shown that this function f hat over here is well defined and is also linear. So by the argument from earlier in the video, that proves that these elements of the tensor product are linearly independent, and therefore that this set forms a basis for the tensor product. So if ei is a basis for v and fj is a basis for w, then ei tensor fj is a basis for v tensor w. I wanted to make this video to show an example of how we can apply the universal property of the tensor product to some important properties of vector spaces. In particular, in this case, we were able to use this map f hat to prove that these elements of the tensor product form a basis. But in order to use this f hat, we need to know that it's a well-defined linear map. And that's often the hardest part of any type of function definition on tensor products. Anytime we define a function on the tensor product, we need to know that it's well defined, we need to know that it's linear, and that can be very hard to do in general because of all the relations between elements of the tensor product. But using the universal property of tensor products, we can remove all of that extra work and just look at a bilinear map on the Cartesian product, which is a much easier object to work with. We define our bilinear map, and as long as that is constructed, we can use the universal property to give us the well-defined linear map that we need for our arguments. And at the end of the day, that's one of the most important uses of the universal property.